Hey there, Calc 2 folks, back here with another quick video in our study of vectors and vector operations, where in the last video I highlighted that two advanced vector operations are these cases for the product of vectors, one of which being the scalar product, which we saw was the dot product in our last video. And the other is the case of what we call a vector product, which is the case for the cross product. And that's what we're going to take note on in this video. Now, as I open with, I do note the cross product is a product operation on vectors, right? Producing what is called a vector product, right? A product of two vector quantities that is itself a vector, right? Where for vectors u and v, right, the vector product of u with v is actually a vector, right, that describes orthogonal behavior to both u and v, right, where the magnitude of the vector product, right, is dependent upon the magnitude of u, the magnitude of v, and the angle that happens to form between u and v in standard position, this angle measurement theta, right? What the vector product known as the cross product produces, folks, is that for two vectors in standard position will describe the direction orthogonal to those two vectors. It will describe the direction that meets those two vectors at a perfect right angle, right? And that will be the description of the direction for the vector given, whereas its length will just depend upon what happens to be the length of u, the length of v, and the angle between these two vectors. Right? We do see this in formal definition, right, where we see the beginning of our notation here. For two vectors u and v, the cross product of u with v is denoted as vector u, where we see this cross multiplication symbol used as opposed to what we saw for the case of the dot product. In the dot product of u and v, we used a dot multiplication symbol. When working with your dot and cross products, you do want to pay attention to this symbol, the symbol of the product. Back in our elementary school days, right, we learned early on about this cross product symbol as just meaning multiplication. It was soon replaced with the dot product symbol in our multiplication, but both of them do mean different products when we get to the realm of vectors. And even different from what we understand as being just scalar multiplication, where we have a scalar quantity times a vector quantity, right? Well, here we're highlighting vector u crossed with vector v, right, the cross product here, where what this produces is a vector, right, that's orthogonal to the plane containing both u and v in standard position. If I put vector u and vector v in standard position, they will exist within a plane together, right? A two-dimensional plane will contain both u and v at the same time. Well, the cross product is a vector that's orthogonal to that plane, right? Where the direction is determined by what we call the right-hand rule, and I'll explain that here in a moment with an illustration, but the magnitude of the cross product is the magnitude of vector u times the magnitude of vector v times the sine of theta. Theta, again, being the smallest angle forming between u and v. Theta being some angle measurement in this interval from 0 to pi. Right? So the cross product of u and v is a vector, right, that's orthogonal to the plane containing u and v, whose magnitude is calculated using this product of the magnitude of u with v times the sine of theta. If we were to illustrate this in three-dimensional space, this would be our illustration here, right, where this is highlighting in this space vector u and vector v, where you will take note for any two vectors that happen to fall in standard position, right, sharing their tails on their vectors at the origin of the system, or what we might say just really is at some common location, right? Those two vectors u and v will always fall in some plane in that space, and that's what we see happening here. Vector u and vector v define or fall within this plane, where their cross product is this vector seen here, right, that is actually meeting the plane at a right angle. It is intersecting that plane, orthogonal to that plane, and orthogonal to the vectors u and vectors v in that plane, right? The cross product will always be a vector orthogonal to our plane containing u and v. It'll always be a vector orthogonal to u and v, right? Now, how long is this vector u and v, or u crossed with v? Well, that depends upon the length of u and the length of vector v individually, and what happens to be the shortest little angle here that is forming between u and v in this arrangement. All right? Now, how do we calculate that cross product? Well, let me explain right-hand rule real quick. The right-hand rule, right, is a rule that we use to determine the direction of this orthogonal vector. Now, how the right-hand rule is applied to understand this direction is if I was to place my right hand, it's always your right hand, flat on this plane, right, with my fingers, my uncurled fingers, my hand kind of laid out flat but on its edge, with the thumb pointing in the direction of u crossed with v, the fingers on my right hand would curl through the angle from theta, or will curl through that angle theta from u to v, and as it curls from u to v, my thumb will point up here in the direction of this cross vector, right? If I was to place my right hand on its edge along vector u and curl my fingers in the direction of vector v through that angle measurement theta, my thumb will point up in this direction, which would be the direction illustrated by the cross product. You will notice then, if you change the order in this cross product, instead of having u crossed with v, you had v crossed with u, and you applied the right-hand rule, the vector would actually point in the opposite direction, downward, and in this illustration. If I was to consider moving to the other side of the plane, below this plane, that's where I would have to be to place my right hand against the plane, where my fingers would curl on my right hand from v to u through that angle measurement theta. And as my right hand placed so that my angle onto this plane, so that my fingers curl from v to u through theta, theta being the shortest angle, my thumb would actually point in the opposite direction of what this vector is currently pointing. All right? So that is what's called the right-handed rule, right, for determining the direction of the cross vector, or the cross product, this vector product, right? I do believe there's a good illustration of that in your book. This is a little hard to illustrate in the video here two-dimensionally, all right? Now, how do we calculate that cross product? That cross product's calculation does depend upon a theorem, right? A theorem that does vary a little bit from 2 to 3-dimensional space, but actually doesn't vary that much. If you were to break down the actual 3-dimensional calculation, you would see this would be the result. Now, in the case of 2 dimensions, if vector u is equal to the 2-dimensional vector u1, u2, and vector v is the 2-dimensional v1, v2, and these two vectors exist in 2 dimensions, the x, y coordinate system, The cross product is still going to be a three-dimensional vector description. The direction orthogonal to the xy plane is going to be up and off into the direction of the third dimension, right? So what we do see is the result of this cross product is itself a three-dimensional vector. Now that direction orthogonal to the xy plane in two-dimensional space where these two vectors exist does not have a description that with respect to x or with respect to y. That description is solely with respect to the direction highlighted by the z component here, where the magnitude we can see here is going to be given by u1 times v2 minus u2 times v1, right? The value of this third component, which will just correspond to the magnitude of this cross product, is just coming from taking this first component in u and multiplying it by the second component in v. That's u1 times v2, and subtracting from that the second component in u times the first component in v, right? That z component will be given by that value where the x and the y will take on the values of 0 respectively, right? And again, note the cross product of u and v in R2 is a vector, again, in three-dimensional space that is orthogonal to this xy plane, where the magnitude actually corresponds to this value, right? And maybe we could add that in here, or we might say here, where the magnitude of vector u crossed with vector v, right, equals this quantity here, right, in our two-dimensional space. Let me catch the one at the end there. Right? That would be our magnitude for the cross product in this two-dimensional description, and that magnitude does correspond to the component in the z component in the description of the cross product in the cross product vector, right? In three-dimensional space, it does get a bit more complex, folks. All right? It is a formula that you're going to have to really just relearn to rely upon, and after a while, you might develop the pattern that you have to follow in this formulaic calculation, right? In R3, u bar, the vector u will be equal to the component vector u1, u2, u3, and vector v will be equal to the component vector v1, v2, v3. And the cross product of u with v, right, will be given also by a three-component vector, where now this time around, you do have respective descriptions for the x and the y component. You will notice that the z component is the same as what we've seen above, right? The z component there is the same as what we see up here, right? But there is also a respective x and y component, where in the x component, you are going to take the value of u2 times v3 and subtract from that u3 minus v2, right? That will form your first component in the cross product. And notice that involves u2 and v3 and u3 and v2 in its calculation. There's a bit of the pattern starting to show itself. Whereas in this second component, for the y component, right, you are going to take the opposite of this quantity. This quantity involving u1 and u3 and v1 and v3, where it's going to be the opposite of u1, well, opposite of the quantity given by u1 times v3 minus u3 times v1. Right? That will form your y component, and then your z component, the third component, is that familiar component from the two-dimensional calculation. What you would notice, though, in terms of how the 2 relates to the third dimension, is if you would just add a 0 component to these vector descriptions, or really we should say a z component of 0 in value to these descriptions here in two-dimensional space, and you perform this third-dimensional calculation, this calculation of the cross product in third dimensions, when you calculate these values using these zeros in these third locations and these third components, these will result in zeros for these 2 components, giving us these zeros in these first 2 locations. So recognize that this description of cross product in this two-dimensional space really is just a simplistic case of having a 0 component in these third locations, a 0 value in these third components of our vectors u and b. All right. One other thing we note about the cross product calculation, right, is it is what we call a determinant calculation. If you go back and recall some of your college algebra, and if you calculated any college algebra, if you've had a linear algebra course, or you've studied a little bit of linear algebra, all the cross product is what we call a determinant calculation of a 3x3 matrix seen here, where the first row of that matrix is just made up of your standard unit vectors I, J, and K, right, pointing off into the positive x, positive y, and positive z axis of three-dimensional space. Your second row is made up of the components u1, u2, and u3 from your first vector in the cross product u, and your third row is made up of v1, v2, and v3, the 3 components of your vector v, the second vector in the cross product. Where if you've done any determinant calculations for the, what we might say, the first component involving the direction of I, it is going to involve the components u2, u3, v2, and v3, where you are going to form u2 times v3 minus u3 times v2. There's very much a crossing calculation there. It's u2 minus v3 times it's u2 times v3 minus u3 times v2 for your ith component, right? That's this description here. It's then going to be minus the description for the cross product of your jth component, right? The component in the direction of j. So if j is where we're considering calculating the cross product now for this component, it is going to involve the value u1, v3, u3, and v1. You are going to take u1 times v3 minus u3 times v1. That crossing, u1 times v3 minus u3 times v1, where you're going to take the opposite of that quantity and make that your jth component. And then that is going to be added to the value for the kth component, which is going to involve crossing u1, u2 with v1, v2. It is going to be, you are going to add on the quantity u1 times v2 minus u2 times v1. It is this crossing pattern, u1 times v2 minus u2 times v1. That is going to determine this value seen for the third component or the kth component in this standard unit vector notation for the cross product. Again, folks, it's going to come down to practice, lots and lots of practice of calculating cross products. You may even look for a couple of videos out there illustrating just cross product calculations for three-dimensional vectors. Right? There are a couple of different illustrations of of getting through that calculation. And it's a pattern. It's a pattern that you'll develop over time, right? Now, develop an understanding of over time. If we consider doing a cross product then for the vector 2, 5 with negative 1, 4 in two-dimensional space, it is going to be a three-dimensional vector where the first two components are just 0, 0. But that third component is going to come from 2 times 4, which is 8, minus negative 1 times 5, which is negative 5. So you're going to take 8 minus negative 5. And 8 minus negative 5 is 8 plus 5, and that is 13 in value. So the cross product here of u with v in this case is just 0, 0, 13. Right? This vector orthogonal to this xy plane, whose magnitude is 13 in value. If we consider the cross product in a three-dimensional calculation, again, this is all just the formula given above, right? For u bar given by negative 1, 6, and v given by, vector v given by 2, 0, 5, the first component here, right, you'll see comes from just negative 1 times 5 minus 6 times 0. Right? Well, negative 1 times 5 is negative 5, minus 0 times 6 is 0, right? So it's just going to be negative 5 for the first component. In the second component, it is going to be the opposite of a similar pattern involving the first and third terms. It is going to be 7 times 5 minus 6 times 2, whatever the opposite of that cross product is, right? 7 times 5 is 35. 6 times 2 is 12, so 35 minus 2 is 23, but it's then the opposite of that. So it's negative 23 in value. All right? And then lastly, for that third and final component, that comes from the first two components of each vector in that crossing pattern. It is going to be 7 times 0, which is 0, minus negative 1 times 2, which is negative 2. So it's 0 minus negative 2. Well, 0 minus negative 2 is 2 in value. Right? That is the cross product calculation there, folks. And it is just following that pattern in its calculation. You may just have to memorize the formula, folks, or after a while you will start to develop that cross product calculation. And the biggest mistake is neglecting the negative value in the middle component. It is going to be the opposite of that cross product pattern. In both this component form and the standard unit vector form, you're going to want to remember that minus. That is some of the biggest mistakes that students make. Take note. Now, we do see a bit of quick application to wrap this up, right? The cross product can actually be used to describe torque, right? Where what is torque? Torque is a description of a twisting or rotating force at a point, right? In three-dimensional space, if the tail of a radial arm exists at a point and is described by the vector r bar, that radial arm being described by the vector r bar, and a force vector described by big F bar is applied to the head of that radial arm, right? Then the torque produced by the force at that point applied by that radial arm, right, is actually going to be given by the magnitude of the cross product for vector r, the radial arm's description, with the force vector description, right? And that magnitude will be the actual measurement of the torque. Whereas there is going to be a related direction for the cross product seen here, r bar crossed with f bar. The actual direction described by r bar crossed with f bar is describing the axis of revolution for that torque. As I said, it is a description of a twisting force. The actual measurement of the force, the twisting force, the torque, is the magnitude of this cross product, whereas the direction of the twist is going to happen around an axis of rotation described by the direction that this cross product is illustrating. All right? So the direction illustrated by this cross product is the direction for the axis of revolution or rotation in this description of torque. Now, if we look at a quick example, right, you go, well, what could be a quick example? We might consider calculating the torque applied by a screwdriver, right? A screwdriver is this tool we use that creates this twisting action, right, at its head, right, where the handle might have a radius of 1/4 inch. You know, the part that we grab on the screwdriver that we actually hold on to as we twist our wrist, right, to screw in a screw or to unscrew a screw, has a radius of 1/4 inch. So that might be thought of as a little tiny radial arm there. From the center of your screwdriver to the edge of your handle might be thought of as a little tiny radial arm, right? Where if it's only 1/4 inch in radius, that's about 1/48 of a foot, right? 12 inches in a foot, 1/4 inch makes about 1/48 of a foot exactly, right? And let's say that as your hand or your wrist twists that handle of the screwdriver or twists that radial arm measuring 1/4 of an inch by a force of 3 pounds, where it's being applied orthogonal to the handle, meaning at a right angle to the handle. We might consider that as the behavior of our hand as it twists that screwdriver handle. It really is applying that force, we might say, in its full potential, which would be at a direction orthogonal to the handle, right? The edge of the handle, or the edge of the radial arm, we might say, that is forming the handle, right? Where in this case, then, we might say that that torque is nothing more than the magnitude of the radial arm, which is 1/48 of a foot. And I'm measuring a foot for a very specific reason we'll see here at the end. The torque is being measured in pounds, 3 pounds, so its magnitude is actually 3 itself. And because we're applying it orthogonally to the handle or to the radial arm, that would be at a 90-degree angle. So it would be the magnitude of 1/48 times the magnitude of 3 times the sine of 90 degrees, which is really just 1/48 times 3 times 1 in value. Now, I should be terribly careful here. This should be, let's be a little careful. This is not, let's be general here. Let's call this is not the true magnitude there. The magnitude of actually that, these aren't vectors, so I got to make sure I have vector descriptions in there. So I'm just going to call these our R bar and our F bar, right? Where their magnitudes are actually given by these measurements, right? This is the length of R bar. This is the magnitude of the force being applied, 3 pounds. And it's being applied at an angle that's orthogonal, which is 90 degrees. So I'm going to lay this out rather general in this statement here, where then if we fill in 1/48 for this, we have this. If we fill in 3 for this force magnitude, we have this. And then the sine of 90 degrees we know is 1, so really it's just 3 times 1/48, which simplifies to 1/16. And if my measurements are in pounds, or if my force is in pounds and my distance is measured in feet, then we can call that description of force here with respect to distance being a measurement of foot-pounds. We call this, might say here we have 1/16 of a foot-pound of torque being applied by the screwdriver's handle. All right? So torque is some physical application where we actually make use of this cross product. And along with the use of cross and dot products, folks, these are going to have a lot of applications come back up in your Calculus 3 study. As we go on to study vector-valued functions and motion in space, we're going to use cross products and dot products. And as we continue on through into vector calculus at the end of Calc 3, right now my Calc 3 students are studying that vector calculus at the end of the book, and they are using dot products and cross products rather heavily in that study, right? So these ideas, these vector operations are some fundamental operations. They're a little bit more complex in their calculation at times, and they do have a little bit more of a complex understanding than your typical scalar value understanding of multiplication or products. But they are going to be also very quite useful to us and become part of our mathematics as we move on in our study of the calculus, and as we move on really into our study of algebra too, linear algebra. You're going to see dot products and cross products used quite frequently, right? So, folks, with that said, I will go ahead and end the video there. I will take note, there are some quick properties of cross products that I do make quick note of down below here. You might want to read through these cross properties. One of the biggest one is that if you switch the direction, you do get the opposite of what you would normally calculate. You would get the opposite vector in terms of the description of its direction and in terms of its description of direction, right? Cross products, scalar values of a cross product, or we might say here, the cross product of these scalar values of two vectors is really just the product of the scalars times the cross product of the two vectors, right? And then a cross product operator will distribute itself over a sum of two vectors when the sum of two vectors is the second vector in the cross product, as seen here, and a cross product will distribute itself across the sum of two vectors as the second vector in the cross product, as seen here. So there are also some quick properties here you can take note of. One of the biggest ones is being that's, watch the order of your cross products. Changing the order does change their value, folks. Take note. All right. These other properties might come up, usefulness, useful in your theory down the road, but they're not, again, they're just properties. They're the things we want to take note on in terms of how do cross products behave. All right. So, folks, again, that is the notes here on cross product. Again, we're looking here just at vector operations, and this is the the product of two vector operations that produces what we call a vector product, or this product that is known as this product of two vectors that itself is a vector description. And again, what that vector description describes is a vector that is orthogonal to the two vectors in the cross product, where the length of that vector, given by the cross product, that is orthogonal to the other two vectors, depends upon the angle between the two vectors and the length of the two vectors themselves. All right? So, folks, I will end there. I hope you're hanging in there. We don't have much left to discuss. I'm going to be back with some quick notes over looking at some common surfaces and lines in three-dimensional space. We're going to look at the plane and the line in three-dimensional space, which is going to make use of some vectors in their definitions. And then we're going to look at using the conic sections to talk about some quadratic surfaces and other common surfaces we're going to encounter in a three-dimensional space. That's going to kind of prep us up for the study of multivariable functions back in Calculus 3. All right. So I will stop there. Hope you're hanging in there, and I will see you next time.